In 20-2, we started talking about parallel versus series circuits. Then in 20-3, we put those together into a circuit that had both parallel and series components to it. We learned how to simplify these circuits. We looked at our laws of circuitry. So in order to discuss this, I'm going to go through a math problem that facilitates all this. So let's say let's start with series, then we'll go to parallel. This is what I did in the other class, and I think it worked really well, because we can talk about the theory as we go through the math. So we're going to draw ourselves a simple series circuit. A series circuit simply means that it's a continuous path with no branching off or any junctions anywhere. So let's say this is our circuit right here. The battery supplies 9 volts. The first resistor is 2 ohms. The second is 3 ohms. The third is 5 ohms. Now, I just arbitrarily came up with these numbers. You can do the same. So when you're practicing tonight and you want to recreate an example to practice, this example that I'm going through now is a great model to use. You would just, vary the number of resistors and the resistances themselves. So, here's what a problem like this would say. A problem like this would say the following. Determine the current in the circuit. Then determine the voltage drop across each resistor. Okay? Let's say determine the current in the circuit overall, not across each resistor, the current in the circuit. Then determine the voltage across each resistor, the voltage drop. Now, correct. But I'm going to use this to explain a lot of the theory as well, because the theory comes from the circuits themselves. LT. So when you make an example on your own, just change the amount of resistors. Maybe make this 2, make this one 7, make this 9. It doesn't matter. Anything you want to choose as numbers, just not negative numbers. Okay?
Are there so many voltages across
each resistor, the voltage drop across each resistor. So, to start this problem, we need to find the current in the whole system. What formula relates current, voltage, and resistance?
I equals V over R?
Yes, which comes from V equals IR, from Ohm's law. This is our governing equation. V equals IR. V equals IR. Now, this equation can be utilized either for individual resistors or the entire circuit. So, if I said to you, find the current in the whole circuit, well, I need the voltage for the whole circuit. Well, what is that? What's the voltage for the whole circuit? 9. It's right here. But what's the resistance for the whole circuit is where our laws come into play. Okay? Now, we see that these are in series. And in series, we think about the flow in a pipe going around a room. If that pipe doesn't branch off, the flow is going to be the same at any point in time. So that's the same idea here with current. The current across each resistor is going to be the same. It does not matter. So we're going to try and find the current in the whole system so then we can use that current for each individual resistor. Well, to find the current in the whole system, we need the resistance in the whole system. Our resistance law says the following. And this is in series. Okay, it's a sum law. It's a sum law. If you don't have this, you don't have to have it memorized, but if you're not familiar with this, if you're not familiar with what I'm writing in the bottom right, this is coming straight from your formulas from this chapter, from 20-2. It's also on your formula sheet on the bottom. I think I use S for series and P for parallel on your formula sheet. So if you look at your formula sheet now, I think I wrote RS, resistors in series, equals R1 plus R2 plus dot dot dot. Okay, it's a sum rule.
We need to say, I know we have to add up all the things. So I have to say we have to add them all up because this law says we have to. Okay?
No. You would do the math. Yeah, just do the math. So, as a result, since the equivalent resistance of a circuit that's in series is really just the sum of those resistors, we can redraw this circuit with one resistor, taking the place of the other three. And since our law says to sum them together, we simply write 10 ohms. Where does the 10 come from? 2 plus 3 plus 5. Resistors in series, sum them together. That gives us the resistance for the overall circuit. Well, I've got the voltage for the overall circuit also. If I've got the voltage and I've got the resistance, what third piece can I always find? The current. Look at the top right. Use the formula in the top right now. The voltage is 9 volts. The current is unknown. The overall resistance is 10 ohms. So the current will be 9 divided by 10. There's the current in the system. Okay, less than 1 amp of current. Very low current. Remember, please, actually, I'll wait on this. I'll talk about it in the next example. So we've got the current in the entire system. What was the second part of the problem that I asked? What was the second part I asked about? Sam, what did I say after that? The voltage in each resistor. The next part was find the voltage drop across each resistor.
Isn't the voltage the same?
That's in parallel. Be careful. In parallel, the voltage is the same. In series, it's the current that's the same. But take a look. I know the current in the entire system. 0.9 amps. That's the current across any resistor. Because I1 equals I2 equals I3, etc. for series. So because this is the current in the system, and I've got the resistance for each of these resistors, use V equals IR for each resistor. Let's go ahead and use V equals IR for each resistor. I'm going to do that over here. So the voltage across the first resistor is the current across the first resistor times the first resistance itself, which is V equals IR. But because we're in series, the current for all of these resistors is going to be 0.9. Well, the first resistor I'm going to use as 2. Okay, the top one. So the voltage across the first resistor is 1.8 volts. Again, remember please that the circuit technically flows out of the positive terminal and in this direction always. Again, the circuit flows out of the positive terminal and back into the negative terminal. So this is the first resistor, I called it V1. How do I get V2? Tom?
You just use a different resistor?
Exactly. It's the same current for V2, it's still 0.9. But now we use 3 ohms for the resistance. And I get 2.7 volts. And then last but not least, the third resistor, 0.9. Remember that the current in the system that you solve for in series is the same as the current at any point in time. The flow in the circuit in series is always the same. So if you get a current of the whole system, you could utilize this number for all of your resistors if they're in series. You're solving for the voltage. 4.5. What do you notice? What do you notice that's not a coincidence? They add up to 9. Why do they add up to 9? Yeah, the voltage of the entire battery is 9 volts. Well, voltage in series is the sum of each voltage drop, totaling the voltage provided. Well, look, the first resistor uses 1.8 volts. The second resistor uses 2.7 volts. The third resistor uses 4.5 volts. Altogether, they use up 9 volts. 9 volts. Okay, in the other class, somebody asked the question, sometimes voltage is called potential difference in the text. Why is that? Okay, let me answer that real quick. Do you know why?
I'm going to assume it's because because if you look at it, each time you're taking, you're subtracting from I call it subtracting from the battery, like it's like when you use your phone. So like if you use it for 2 minutes, you're taking that time off the battery, and like you use another 3 minutes, and it's another subtracted from what's left. Like you subtract 5 from what's left.
So difference is good, but why potential difference?
Because you may not use up it's the potential to lose it, so it may not use up all the.
You're on the right track, yeah. You're on the right track. It is the potential to lose that energy. Remember when we looked at circuits, we talked about charge carriers having a lot of potential energy when they exit the battery? And then what happens when they hit a bulb? The potential energy drops, doesn't it? And then it gets back to the battery does work, it charges it back up to high potential. So really, at one end of this circuit, right here at the top, when the charge carriers leave, they have high potential. Lose some potential, lose some potential, lose the rest of your potential, getting back with no potential energy. Then you get recharged, and then you go through the circuit again. So it's called the potential difference because from one terminal of the battery to the other terminal, your potential energy differs. There's a huge difference of 9 volts. So the word voltage and potential difference is the same thing. Okay? Same thing. Now, this was everything in series that we talked about here. This was everything in series that we talked about. Recognize that your resistance is a pretty large value. You added them together. Because the resistance was a large value, the current was a very low value. Resistance and current. It's a balance. They're inversely related. Very good, Tom. If you have a lot of resistance in the circuit, your current has to be low. If you have low resistance, which we're going to see in a minute with parallel circuit, the current is going to be really high. Okay? So this was our summarization with series. Okay? With series. If you can do an example like this, you should be, relatively good. A follow-up, a part C, could be something like this. Determine the power generated or used or consumed by bulb 1. Resistor 1, whatever, bulb resistor. How would you find the power consumed or used by the first resistor? How do you find power? You could use that from the previous chapter, but it wouldn't help here. There was 3 formulas for power that we could have used. There were 3 formulas for electrical power. Sam gave us the definition for mechanical power, which you could use really, but it'd be a lot more work to do it. One of them was squared for sure. We don't have to use that one, but one of them was definitely squared. Give me one of them.
Power equals I times V.
That's the easiest one. P equals IV. It's on your formula sheet also. So if you do all this work, right, and you determine the voltage across each of these resistors, well, how do you find the power? Power is current times voltage. Please take a look. The current for each resistor is the same, isn't it? 0.9, 0.9, 0.9. So that's not what's changing. What's changing is the voltage across each of these resistors. The resistor that uses more voltage is really using more power. Because it'd be 0.9 times 1.8 is the smallest amount of power. 0.9 times 2.7 is the medium amount of power. 0.9 times 4.5 would be the largest amount of power out of all 3 resistors. So it's easy to see that in these cases, the power is really a function of the voltage or the resistance, not the current. The current is the same for all of these. So if you're trying to find power, you're going to be looking at current times voltage, recognizing that the current is the same. So it's the voltage changing that affects your power level. Let's look at an example of this in parallel now.
Wait, so I'm sorry. What voltage would you use for power? The largest one?
It depends on which resistor you're looking at. If I said find the power through the second resistor, you use the voltage across the second resistor times the current. It's an individual basis, each one. use the same numbers. Okay? What was it? 2, 3, 5?
And then we'll go.
I'm going to do this to emphasize the difference in parallel and series circuits. I want you to see that the resistances are absolutely the same, yet our answers will be very, very different. First, recognizing this is parallel because of the branching right here and right here. These two branching locations are what tell me this is parallel. As soon as I see a branching off, I think parallel. And I think of water flowing through a pipe. Water flowing through a pipe that branches off, part of the current of the water will go one way, part of it will go the other way. So immediately we should recognize that the current is not the same throughout each resistor here. Whereas in series, the current was the same for each. Here, the current splits. It branches off. So, before we do anything, we have to know what the question is asking. Here's what the question would ask for this. The beginning would be the same. Determine the current in the overall circuit. Second part would be what differs. We would say determine the current in the overall circuit and then determine the voltage drop, then determine the current in each resistor or across each resistor. So determine the current in the overall system, then determine the current across each resistor. That's what this problem would state. Now, with that said, we have to simplify the circuit first to determine the current in the overall system. So I need to come up with an equivalent resistance again. I need to do this. I need to figure out what should go right there for this one resistor that will replace the 3 above. Tom, tell me how I start this.
You would add, you do 1 over R for, so you add all of them, then you would 1 over R for each. And then you would do the inverse of the final answer.
Okay, so I have to use my reciprocal sums. Tom recognizes that it's 1 over R. So when I add together those 3 fractions, I have to take the reciprocal or the inverse of that answer. So 1/2 plus 1/5 plus 1/3. That's going to be 0.5, 0.2 is 0.7, 0.3. It's going to be 1.03 repeating, but I need to do the reciprocal of that, or the inverse. So add together your 3 fractions, and then hit x to the negative 1, or just do 1 over that answer. Chris, what do you got?
0.97.
Oops, not current. Resistance, whoops. Resistance. So the equivalent resistance that we're going to utilize is 0.97 ohms. So let's pause for a second and really differentiate between series and parallel. Look at the resistance. The last problem we did this, what was the equivalent resistance? 10. We added 2, 3, and 5 and got 10. Now, we get not even 1.
It's broken up into pieces.
The resistance, when in parallel, decreases for the equivalent resistance because of the reciprocal sum identity. Again, this equivalent resistance, 0.97, is less than any of the resistors we started with. Whereas for series, the equivalent resistance would be greater than the 3 that we started with. With that statement made, with low resistance comes what? With low resistance, higher current. Higher current. So let's solve for current. Voltage over resistance.
Would you say it's because it's the reciprocal, or would you have to say it's a result of the reciprocal property?
No. That's the reason why I'm explaining it to you. Okay, but you don't have to make that statement in the problem. What do you get for current? 9 over 0.97. It's not going to be 10. It's going to be a little bit less. 9.3. My units are amps again. Amps. So that means that coming out of this battery right here, take a look. flowing out of the battery is some current in that direction. This current flows through this actual circuit and back to the beginning with 9.3 amps. Well, how much of it goes here? How much of it goes here? How much of it goes here? We don't know yet. It branches off. This current is not the current throughout each resistor. It's the overall current coming out of the battery. So this 9.3 amps is very high compared to the current in the previous problem, because part of this current goes to each resistor. How much? How do I figure out how much current goes to each resistor?
You use V and then the resistor for each one separately.
Yeah, you use V equals IR for each one separately. Now here's the problem though. I'm trying to find I. Well, R is given to me, isn't it? The first resistance is 2 ohms. We're trying to find I. What's the voltage? Tom? Why?
Because the voltage is the same across each
Resistor.
resistor.
In parallel, the voltage is the same across each resistor. Whereas in series, we had to split up the voltage. Now we're going to be splitting up the current in parallel. That's where those laws switch. You have to remember that they switch. So the overall voltage in parallel is the same as the voltage supplied by the battery. Remember how in series, the voltage was kind of like, it was 9 volts. We had 4.5 for one of them, 2.7 for another, 1.8 for the third. They all added up to 9. In parallel, there's no adding up to 9. The voltage across every resistor is the same. It's whatever comes out of the battery.
Okay.
It's the current that's going to vary here. So what do you get for I1?
4.5 amps.
Yeah, 4.5 amps. Notice the number 4.5 appears again. In the last problem, though, it was 4.5 volts. That's the first resistor. The second resistor, well, we're still going to use 9 volts for V2. The second current times the second resistance, which is 3 ohms.
Is it going to be the same, 2.7?
This one is going to be not the same, actually. This one is going to be just 3, right?
Oh, yeah.
And it has to add up to the amps, right?
Yeah, the total of the currents has to add up to the sum of the currents. So those are the first 2 resistors. That's resistor 1 and resistor 2. The third resistor is also 9 volts, but its resistance is 5 ohms. Jeez. Take 9 divided by 5. 9 divided by 5, 1.8. Is that right? 1.8?
Yeah.
I didn't even do the math. I just asked myself how much is missing from the total. The total was 9.3. I just subtracted these two and got 1.8. Because I know that if I add up these currents, I'm going to get 9.3. 4.5 and 3 is 7.5. That makes 8.5. Another 0.8 makes 9.3. So in parallel, we recognize that the overall current is equivalent to the sum of the currents in the individual resistors. Okay?
What about density?
Yeah. Now, before we get to chapter 9, in section 20-3, this is what you're going to be taking. In 20-3, you're going to have to reduce a complex circuit. Similar to the last question you did in your lab.
Oh, like parallel and series?
Yeah, similar to what you did in the homework as well. Okay, you had 1 or 2 of these in the homework also. So let's say we've got a battery. Out of the battery, it splits right away. From there, we have a resistor here and here. Another one right here. And then back. Let's go with values. Let's say this is 2, 3, 4, 5, and 6. Let's say the voltage supplied is an outlet 120 volts. So let's say this is our setup. This setup is very common. We're going to see, with outlets. There are two outlets here. And these two outlets run on one network, and then if you put a splitter, that splitter branches it off into parallel networks. So this would be the equivalent of like a splitter somewhere. Well, here's what I'm seeing. So just follow my thought process, please. Here's what I physically see. Ready? Charge carrier leaves the positive terminal. Follow, 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 split. Right there. We all see that, right? That split means what? Good. These are parallel with each other. Is that clear? Again, these are parallel with each other. Then they come back together. And then what do I notice here? Split. Which means this is parallel with this. What about these two here? These are series because there's no split between them. Okay? So, these are parallel to each other. These are parallel to each other. This is series. If I can reduce this to one resistor, reduce this to one resistor, these are then in series also. Okay, so the first thing I want to do is simplify this and this. So I'm going to redraw this diagram. Remember, this is how you have to do it. Redraw the diagram every time. Up here, I need one resistor. Here, I need one resistor. And here, I already have one resistor. This one is known. That's 5 ohms. How about this one right here? What should it be, everybody? Why do you know that? Atom, it's in series. So put a 10 here right away. That one's done. The one on the top is the tougher one because it's in parallel. 1 over 3 plus 1 over 2 equals 1 over R. That's what I'm doing for up here, in case it's not clear. Okay, for that pink portion that I've circled, it's 1/3 plus 1/2 equals 1 over R. What does R turn out to be, Chris? Thank you. So we replace it with 1.2. Chris, how do you know that 1.2 is a reasonable answer? How do you know it's not unreasonable based on what you started with? It's less than each of the resistors. Remember, in parallel, the resulting resistor is always less than the one you started with. But in series, the resulting resistor is more than what you started with because you're summing those. Do you have a question or you're going to answer that also? Okay. So we've got 1.2 there. Now we take a look at this new circuit and we say the following. Well, you know what? Series, parallel. Right there. There it is. So these two are in parallel. So let's do it again. Let's take 1 over 10 plus 1 over 5 and set that equal to 1 over R. And we'll replace that circled in white area with our answer for this. Okay, you could do these almost in your head. 1/10 is 0.1, 1/5 is 0.2, it's 0.3. 0.3 is 3/10. Right? 0.3 is 3/10. Invert that. What are we going to get? 3.3 repeating. So I'm going to replace that. So I redraw my circuit. That's 1.2 still from the last part. This is now 3.3 here. And it comes back to the beginning, which is 120 volts. Finally, the last two resistors are in what? Series. So our final answer is going to be 4.5 ohms.
And then you have to find each part.
I may ask you something like, determine the current in the whole circuit. Well, you got voltage, you've got resistance, V equals IR. That's it. But I'm not going to ask you to find stuff across individual resistors because, believe it or not, it works differently working your way back, or it's a little more complex.
Sorry.
Stretch. Okay, let's get to
You would ask us what? Like
find the current in the overall system.
Okay.
using the voltage you have here and the resistance you came up with. All right, buoyancy problems. You want to consider several things. First, and did I go over the steps with you guys or no? Start by drawing free body diagram, FBD. Draw a free body diagram. I'm telling you now, there was one homework problem where the submarine was accelerating. I'm not going to have problems where it's moving. So either it's going to be submerged underwater or floating on top of the water. In both of those scenarios, you've got the weight pulling down and buoyancy pushing up. For the scenario where it's sinking, versus floating, tell me what you know. It's the same free body diagram. If it's floating or sinking, it's the exact same free body diagram. Unless we have, like, remember, a cable attached and there was tension. That stuff you have to, like, incorporate into the problem. What do you know? Give me something.
If you're sinking, it means that your density is greater than the water density, and it also means that gravity is greater than the void.
Those two things are true. Okay, let's write those both down. The density of the object is greater than the density of the fluid. That's what causes the egg to sink. Then you start adding salt, which varies the density of the fluid, which causes the egg to rise. That's that extra credit you could have done. The weight of the object has to be more than the buoyancy if it sinks. Okay? If it sinks. We know one other thing actually too. What else do we know if it sinks? If it sinks, what else do we know?
F9 is equal to F3 minus F2.
Correct. That's always true though, because the diagram here, right? But there's something else actually, Ant. One more thing. Has to do with volume. Close. You're on the right track.
The volume of the object is greater than the volume of the water.
If it's fully sunk,
Sorry.
it's equal. Again, think about it, guys. Archimedes' principle tells me if an object sinks all the way or sinks underwater, the water displaced is equal to the volume of the object. That's how you measure the volume of a rock. So the volume of the object when sunken is equal to the volume of the fluid displaced. This is when it sinks. When it's floating, we know that the density of the object is less than the density of the fluid. If they were equal, it would be kind of hovering in the middle there, okay? We're going to look primarily at sunk and floating. If this is also the case, then the buoyancy balances gravity. Buoyancy cannot be more than gravity, or else it would buoyantly float out of the water. It wouldn't make any sense. And then finally, the last part, the amount of volume displaced in the fluid is going to be less than the volume of the object if it's floating. You have two examples to practice. You have examples from class. Please, please, please practice 9-1. That's going to be your tougher part for your math, I think.